The boom arrives without warning. 1 second, Yosemite Valley is silent beneath the stars. The next, the darkness detonates. Campers jolt awake inside tents. Hikers freeze on remote trails. The sound rolls through the granite walls like artillery fire, echoing across a stone cathedral. Was it an earthquake? A hidden avalanche? A military aircraft? Or something stranger hiding deep inside the Sierra Nevada wilderness? Why do so many disappearances in Yosemite National Park happen in steep granite terrain, shaped by collapse, fracture, ice and unstable geology? Why do witnesses so often describe confusion, sudden weather changes, strange echoes, disorientation, or the feeling that sound itself behaves unnaturally inside the valley? And why do the cliffs sometimes explode in the middle of calm, cloudless nights, with enough force to shake the ground beneath sleeping visitors? The modern mystery surrounding Yosemite's missing people has been amplified by discussions on the Joe Rogan Experience, featuring investigator David Paulides. In those conversations, wilderness disappearances are framed as patterns that appear difficult to explain. Sudden separations, vanishing tracks, failed searches, missing time, loud unexplained booms, vast wilderness swallowing people without leaving clear evidence behind. But once geology enters the picture, Yosemite transforms from a paranormal mystery into something both more understandable and in many ways more terrifying. Because Yosemite is not a stable landscape. It is an active mechanical system built from fractured granite, glacial oversteepening, thermal stress, freeze-thaw, expansion, hydrology, rockfall dynamics, acoustic distortion, terrain entrapment, and constantly shifting mountainsides. The valley is not static scenery. It is a slowly collapsing geological machine, still adjusting to the disappearance of Ice Age glaciers that once buried the entire region beneath moving ice thousands of feet thick. The cliffs towering above Yosemite Valley appear eternal. In reality, they are breaking apart every single day. To understand why the park produces so many strange sounds, dangerous conditions, and difficult search environments, it is necessary to begin hundreds of millions of years before humans ever entered the Sierra Nevada. The granite walls of Yosemite were born deep underground during the age of dinosaurs. During the Cretaceous period, an oceanic tectonic plate was diving beneath the western edge of North America in a process called subduction. As the descending slab plunged into Earth's mantle, heat and pressure released water trapped inside minerals within the crust. That water lowered the melting temperature of surrounding mantle rock, generating large volumes of magma. Those magmas slowly rose upward through Earth's crust and cooled underground over immense spans of time. Instead of erupting violently like volcanoes, much of the molten rock solidified deep below the surface, forming enormous granite bodies known collectively as the Sierra Nevada batholith. Yosemite's cliffs are therefore not volcanic cones. They are the frozen roots of an ancient magmatic system exposed after millions of years of uplift and erosion stripped away the overlying rock. Granite appears incredibly strong, and in compression it is. But granite also contains weaknesses. As the molten rock cooled underground, it contracted. That contraction produced joints and fractures throughout the rock mass. Later, tectonic uplift added even more stress. Then erosion removed thousands of feet of overlying material, allowing pressure release fractures called sheeting joints to form parallel to the land surface. Those hidden fractures are the key to Yosemite's modern instability. When glaciers later invaded the Sierra Nevada during repeated Ice Age cycles, they dramatically transformed the terrain. Massive rivers of ice flowed through existing river valleys, grinding, plucking, and excavating the granite beneath them. Yosemite Valley became a classic glacial trough, steep-walled, deep, and oversteepened. At the height of glaciation, ice may have filled portions of Yosemite Valley to depths approaching 4,000 feet, or roughly 1,200 meters. That enormous mass exerted tremendous pressure against the valley walls. As glaciers moved, rocks frozen into the ice scraped and polished the granite like sandpaper. Other sections were ripped away through quarrying processes in which meltwater penetrated fractures, froze, and helped detach large blocks that were then carried away by the glacier itself. When the glaciers retreated around 15,000 years ago, they left behind cliffs that were mechanically unstable almost from the beginning. Imagine removing giant support braces from the sides of a damaged building. The granite walls suddenly lost the lateral support once provided by thick glacial ice. Existing fractures began opening wider. Stress fields inside the rock reorganized. Entire slabs started slowly peeling outward from the cliffs. That process continues today. One of the most important mechanisms driving Yosemite's constant rockfall activity is exfoliation. In geology, exfoliation refers to the peeling away of outer rock layers due to pressure release and thermal expansion. Yosemite's granite domes and vertical cliffs are full of sheeting joints that behave almost like gigantic onion skins. Some slabs are several feet thick, others are tens of feet thick. Many weigh hundreds or thousands of tons, and many are already partially detached from the mountain. This is where temperature becomes a geological weapon. Granite expands when heated and contracts when cooled. During sunny afternoons in Yosemite, exposed rock surfaces can heat dramatically under direct solar radiation. After sunset, especially in dry mountain air, temperatures can drop rapidly. That daily thermal cycle causes the granite to flex continuously. Researchers from the United States Geological Survey installed instruments inside fractures behind large granite slabs in Yosemite to monitor movement. What they discovered was remarkable. Some slabs physically moved every day. As temperatures rose, cracks widened. As temperatures fell, cracks narrowed again. The movements were small in human terms, but enormous in rock mechanics. Certain fractures shifted by nearly half an inch, or about 12 millimeters, during repeated heating and cooling cycles. That may sound insignificant, but in structural geology it is massive. Rock behaves somewhat like metal fatigue. Bend a paperclip once and nothing happens. Bend it back and forth repeatedly, and microscopic damage accumulates until the structure suddenly snaps. Yosemite's granite experiences a similar process. Every thermal cycle adds stress to crack tips. Every expansion and contraction slightly weakens mineral bonds inside the rock. Eventually, the cliff reaches failure. And when failure occurs, the result can sound like an explosion. This is the origin of many of Yosemite's mysterious nighttime booms. Contrary to sensational stories, these sounds are usually not supernatural events. They are rockfalls. But that explanation does not make them less dramatic. When a granite slab weighing hundreds of tons detaches from a vertical wall hundreds of meters above the valley floor, gravity converts potential energy into violent kinetic energy almost instantly. The falling rock accelerates downward, colliding with ledges, shattering into fragments, and generating shock waves that echo through the valley. Yosemite acts like a natural acoustic chamber. Its steep granite walls reflect sound extremely efficiently. Low-frequency vibrations bounce repeatedly across the valley, amplifying the sensation of a deep, concussive blast. At night, the effect becomes even more intense, because ambient background noise drops dramatically. There are fewer wind sounds, fewer human activities, and cooler air layers can refract sound waves back toward the ground, instead of allowing them to disperse upward. A rockfall occurring miles away may therefore sound startlingly close. But thermal stress alone is only part of the story. Water is perhaps the most destructive force operating inside Yosemite's granite. During daytime warming, snowmelt and groundwater seep into fractures throughout the cliffs. Some cracks are microscopic, others are large enough to fit an entire human body. Once temperatures drop below freezing, the water begins changing phase from liquid to solid. And that phase change is extraordinarily powerful. Water expands by approximately 9% when it freezes. Inside an open container, this expansion is harmless. Inside a confined granite fracture, it becomes a hydraulic jack. The growing ice exerts pressure directly against the crack walls. If the fracture is water-filled and constrained, freezing can generate stresses reaching hundreds of megapascals. That exceeds the tensile strength of granite itself. In simple terms, the ice can literally force the rock apart. This process is known as frost wedging or freeze-thaw weathering, and Yosemite provides nearly perfect conditions for it. The park experiences repeated oscillations around the freezing point during many seasons. Water enters cracks during warmer periods, freezes during colder periods, expands, widens the fractures slightly, melts again, and then repeats the cycle. Each event may enlarge a crack by only microscopic amounts. But geology operates through repetition. Thousands of cycles over decades or centuries can destabilize entire cliff systems. The dramatic nighttime booms heard in Yosemite often occur during the coldest hours before dawn, because that is when thermal contraction and ice expansion may simultaneously maximize stress inside the granite. A slab already weakened by years of flexing and frost wedging finally exceeds its failure threshold. Then the mountain breaks. Visitors often describe these events as sounding like cannon fire, explosions, or thunder emerging from inside the earth itself. In reality, they are hearing stored geological stress releasing all at once. Park records confirm how common this process is. More than 1,000 documented rockfalls have occurred in Yosemite since systematic observation began. Vast talus piles at the bases of cliffs are physical evidence of countless earlier collapses extending far beyond written history. Rockfall is not an anomaly in Yosemite. It is one of the park's defining geological processes. This has enormous implications for wilderness disappearances and search operations. Many discussions surrounding missing persons focus on mysterious circumstances while ignoring terrain mechanics. Yosemite's landscape is extraordinarily hostile to tracking and recovery efforts for purely geological reasons. The valley contains steep talus slopes made from unstable angular granite blocks. These accumulations form when repeated rockfalls shatter and pile debris at cliff bases. Talus fields are notoriously dangerous because the rocks shift underfoot, contain hidden voids, and can swallow objects deep beneath the surface. A person injured inside a talus field may become almost impossible to locate visually from above. Crevices between boulders can descend several meters underground. Seasonal snow can later bury evidence even further. Small debris flows triggered by storms may rearrange surface rocks and conceal remains. Wildlife scavenging accelerates fragmentation and dispersal. In many wilderness disappearances, geology alone can rapidly erase evidence. Dense conifer forests create additional complications. Granite topography funnels hikers into drainages, gullies, and ravines where line-of-sight visibility collapses. Sound behaves unpredictably because cliffs reflect echoes in misleading directions. Someone shouting for help may sound far closer or farther away than they actually are. Cold air drainage at night can also create sudden fog banks and localized temperature inversions that disorient hikers. In mountainous terrain, people often become lost, not because they traveled far, but because terrain complexity destroys spatial awareness. Yosemite's glacial topography is especially deceptive. The valley appears open and navigable from scenic viewpoints. On the ground, however, steep walls, vegetation, hidden drop-offs, and chaotic boulder fields create a fragmented environment where movement becomes difficult and dangerous very quickly. This is particularly important in cases involving temporary separation from groups. Once an individual leaves a trail or moves downhill toward water, granite terrain can channel movement unpredictably. Slabs that appear walkable from above may terminate abruptly at cliffs. Forest cover can conceal ravines until the last moment. Talus slopes can shift under weight and cause falls. Even experienced hikers can become trapped within surprisingly small areas. Hydrology compounds the danger. Yosemite National Park rivers and streams are not gentle waterways. They are high-gradient mountain systems powered by snowmelt descending through steep terrain. During spring runoff, water velocities can become extreme. Cold water immersion rapidly impairs motor control and cognition. A person entering swift water may disappear downstream quickly while leaving minimal evidence. Granite river channels often contain plunge pools, undercut ledges, submerged cavities, and hydraulic recirculation zones capable of trapping bodies underwater for extended periods. Seasonal flow changes may later transport remains far from the original incident site. Search dogs also encounter severe environmental challenges in such terrain. Popular discussions sometimes portray failed canine tracking as mysterious or paranormal. But mountain meteorology and geology offer more grounded explanations. Scent particles move according to airflow, humidity, terrain shape, solar heating, vegetation, and water movement. In Yosemite, steep granite walls generate complex wind patterns. During the day, warm air rises upslope. At night, cold, dense air drains downward into valleys. These airflow reversals can transport scent unpredictably across large distances. Granite surfaces themselves also retain scent poorly compared with soil or vegetation. Talus fields contain air voids that trap and redirect airflow. Streams fragment scent trails further. Temperature inversions may suppress vertical mixing while channeling odours horizontally. A tracking dog entering such an environment may lose continuity not because a person vanished mysteriously, but because atmospheric physics and terrain complexity disrupted the scent field. The same principles help explain why sounds in Yosemite often feel unnatural. Acoustics inside the valley are shaped by geometry. Massive granite walls reflect low-frequency energy efficiently. Echoes overlap and arrive at different times, depending on terrain configuration. A single falling boulder may generate multiple reflected booms that sound like separate explosions. Under nighttime inversion conditions, sound waves can travel unusually long distances with little attenuation. Campers miles away may therefore hear rockfalls with startling clarity while being unable to determine direction. This acoustic distortion has likely contributed to decades of exaggerated stories surrounding strange sounds in the park. But perhaps the most important scientific point is this. Yosemite's landscape is still evolving. People often imagine geological features as ancient and stable. Yosemite is ancient, but it is not stable. The valley is continuously adjusting to stress redistribution that began when glaciers retreated thousands of years ago. Entire cliffs are slowly deforming right now. Modern monitoring has revealed that some large granite masses in Yosemite move incrementally over time. Tiny displacements accumulate as fractures propagate deeper into the rock. Eventually, catastrophic detachment occurs. This means the park is not merely a scenic backdrop for human stories. It is an active participant. When investigators examine disappearances in such terrain, geology cannot be treated as secondary context. It is central to understanding what physically happens in the wilderness. None of this proves or disproves every claim associated with wilderness mystery narratives. There are certainly cases where important questions remain unanswered. Human behaviour, accidents, medical emergencies, hypothermia, wildlife encounters, criminal acts and environmental exposure all intersect in complicated ways. But science does demonstrate something crucial. Many of Yosemite's supposedly inexplicable phenomena are completely consistent with known geological and environmental processes. The booming sounds have measurable physical origins. The unstable cliffs are actively collapsing. The terrain rapidly destroys evidence. The acoustics distort perception. The hydrology conceals bodies. The meteorology disrupts tracking. And the granite itself is slowly tearing apart under the combined forces of ice, heat, gravity, and time. That reality may actually be more unsettling than supernatural explanations. Because there is no hidden intelligence behind Yosemite's dangers, no secret portal, no invisible predator lurking in the woods. There is only geology operating exactly as physics predicts. and geology is relentless. Every winter night, water penetrates deeper into fractures across Half Dome, El Capitan, Glacier Point, Cathedral Rocks, and hundreds of unnamed cliffs throughout the valley. Every freeze expands those fractures slightly wider. Every hot afternoon thermally flexes the granite again. Every season, gravity pulls detached slabs incrementally outward. The cliffs are under constant mechanical attack from their environment. Eventually, resistance fails. Then the valley roars. Somewhere in the darkness, perhaps hundreds of meters above the forest floor, a crack propagates through ancient granite formed during the age of dinosaurs. A slab separates from the mountain. Gravity seizes it instantly. Rock shatters against rock. Air compresses into shock waves. Echoes ricochet across the glacial canyon. Campers wake in confusion. And physics wins one more time.